Welcome to the 6th episode of A Visual Approach to Optics, a Guide for Clinicians, narrated by Dr. John Gorfinkel. In the last episode, we completed 129 out of 277 slides. In the last episode, we finished with this slide in which we defined the prism diopter. A prism diopter is a deviation of an image at 1 meter away from a prism, as seen by an observer on the other side. Prism power varies with the position of the prism because of the way Snell's law operates, in which the angle of deviation depends on the angle of incidence of the incoming light. Glass prisms are generally measured in the Prentice position, in which the incoming light is at right angles to the first face. The light goes through undeviated and is then bent away from the normal when exiting the other side of the prism. Plastic prisms are generally measured using the position of minimum deviation, in which the overall angle of deviation of the two sides combined is minimized. Lenses are just variable prisms with the highest prismatic power in the periphery and the least in the center. The variable prismatic power is what allows lenses to change the divergence of light as compared to simple prisms which can only change the direction. Here we see a convex lens in which the upper half of the lens has an overall base-down prism effect. The lower half of the lens has an overall base-up prism effect. However, the prisms are variable and change from the greatest power in the periphery to the least in the middle. Concave lenses have a different orientation, in which the upper half has a base-up prism effect and the lower half has a base-down prism effect, which is the opposite of that seen in the convex lens. Lens power varies with the orientation of the lens to the incoming light. Like prisms, the orientation of the lens will change the effective power because of the way Snell's law works, in that the angle of deviation depends on the angle of incidence. In this part of the diagram, we see rays reaching the lens, which is oriented at right angles to the direction of the light. Here we see a lens tilted with respect to the direction of the incoming light. This has the effect of increasing spherical power and creating a cylinder in the axis of rotation, known as astigmatism of oblique incidence. This results in the image moving closer to the lens as compared to here, and the image being formed into a conoid of Sturm rather than an image point. Lenses can have prismatic effect where the aperture is not located over the center of the lens as here. When located over the center of the lens, the object is refracted, the image rays are converging and reach an image point which is in line with the object along the horizontal. Here, where the aperture overlies the upper half of the lens, object rays are converged to form an image point, but the overall image rays are bent towards the base because of the base-down prism effect with an image displaced downwards. Here we see in red the overall direction of prismatic effect of the different parts of the lens. The aperture overlying the center of this lens has equal base-down and base-up prismatic effects. However, the aperture overlying the upper half of this lens has a net overall base-down prismatic effect. We can use prisms to correct eye deviations. Here we see left esotropia with the eye deviated inwards. The base out prism is placed and bends the light towards the base so that the virtual image appears bent towards the apex and is now in line with the pupil. Here we have a left exotropia in which the eye is deviated outwards. The base-in prism here bends the light towards its base such that the virtual image is bent towards the apex. The image is now in line with the pupil. What happens if we put a prism over an undeviated eye? Here we have a base-out prism which is bending the light towards the base and the virtual image towards the apex. The pupil has a relative outward position to the incoming light, and this is therefore an induced relative exotropia. Here we have a base-in prism bending the light towards the base so that the virtual image is bent towards the apex. The pupil has a relative inward position compared to the incoming light, and this is induced relative esotropia. What does the patient's pupil look like behind the patient's glasses to an observer? Here we have a prism in front of the patient's eye, and the observer is looking from here. To the observer, the image is bent towards the apex inward. In this case, we have a base-in prism, and the image as seen by the observer is bent towards the apex in the outward position. Note that where the observer sees the patient's eye deviated outwards behind the prism, the patient will see the observer's position deviated towards the apex as well. One may ask, how is it that each party sees the image deviated towards the apex, which is opposite to each other's relative position? The answer is that they are not looking at the same thing. The observer is looking at the patient, and the patient is looking at the observer. Fresnel prisms are a way to reduce the bulk of a regular prism. Here we have small segments in which the overall slope of the surfaces is equivalent to that of the original prism. However, most of the bulk is reduced. The downside is that there are discontinuities between each segment which scatter light and degrade the image. Fresnel lenses can reduce the bulk of lenses in a manner similar to Fresnel prisms reducing the bulk of prisms. In the Fresnel lens, we have an overall curvature that adds up to equal that of the original lens. However, there are the discontinuities with light scatter at the boundaries and some degradation of the image. Here we see a picture of a lighthouse lens, which is a Fresnel lens with much less bulk, but here are the segments with their discontinuities. Prentice's rule describes the overall prismatic effect of a lens if the aperture is located over an eccentric part of the lens. Prentice's rule says that the prismatic deviation is equal to the distance between the center of the aperture and the optical center of the lens multiplied by the power of the lens. The units of the distance are in centimeters and of power in diopters. Here we have a lens located so that the pupil is in line with the upper part of the lens. The center of the pupil is 2 centimeters away from the optical center of the lens. The lens has a power of 2 diopters. Therefore, the prismatic deviation of this lens is 2 times 2, which is 4 prism diopters. It is a base down prism because the pupil overlies the upper part of the lens, which has an overall base down effect. Here we see that the pupil overlies a part of the lens that has an overall base down effect. One may use prismatic shift to check the sign of an unknown lens by moving it upwards relative to the position of the observer. If we put an object behind the lens at a distance closer than the focal point of the lens will create a virtual image for the observer. And this virtual image position will change as the lens is being moved. Here we see the observer's pupil overlying an eccentric position of the lens with an overall base down prismatic effect, so that the virtual image is shifted upwards towards the apex. The lens has been moved up so that the observer's pupil now intersects the lens at a more central location with lower prismatic power. The overall prism is still base down, but the virtual image is now shifted less towards the apex than before. The lens has been moved up further so that the patient's pupil overlies the center of the lens and there is little prismatic deviation of the virtual image, shown in red. The lens has been moved further up and the pupil of the observer now overlies a lower part of the lens with an overall base up prism, so that the virtual image is now shifted downwards towards the apex. The lens has been moved up further so that the patient's pupil now overlies a more peripheral part of the lens. It is still a base-up lens, but it is of higher power, and the virtual image is therefore shifted towards the apex to a greater extent than in the previous slide. The overall effect, as the lens is being moved up, is to have the virtual image move down. Watch one more time. In this case, upward movement of the lens resulted in downward movement of the virtual image. This is against motion of the object behind the lens, which indicates it is a converging lens or a plus lens. If we see with motion of the object behind the lens, so that the virtual image moves in the same direction as we move the lens, that would indicate a minus lens. In order to add prisms, we need to use vectors. So if we went 1 centimeter to the right from the optical center of this lens, and then 1 centimeter down, we would have to add 5 prism diopters this way, with 5 prism diopters this way, using Pythagoras' theorem to get the hypotenuse and trigonometry to get the orientation. We use bifocal glasses for presbyopia, where the distance portion of the lens has a different power than the reading portion. In this example, the distance lens is 5 diopters, and an added segment has 1 diopter of power, for an overall total of 6 diopters in the reading position. When the pupil is looking straight ahead and is aligned with the distance portion of the lens, the eye experiences a 5 diopter lens. When the pupil is lined up with the segment, the eye experiences a 6 diopter effect. We calculate the distance and near prism effect in the bifocals separately and then add them together to get the total effect. In this case, we have a distance lens of 5 diopters, and the person is going to be reading by looking through a position of the lens that is 2 centimeters below the optical center. According to Prentice's rule, we multiply 2 by 5 and we get a 10 prism diopter base up prism, because we are in the lower half of a plus lens. This is for the distance lens. For the reading segment, we have an additional lens, shown here. In this reading segment, we have placed the flat top of the segment, which contains the optical center of this segment, 1 centimeter below the distance lens. The reading position is therefore 1 centimeter below the optical center of this segment, whereas it is 2 centimeters below the optical center of the distance lens. We therefore take 1 centimeter times 1 diopter to get an overall 1 prism diopter base up prism from the reading ad. We then add this prismatic number for the reading ad to that of the distance ad, and we get a total of 11 prism diopters base up prism. Progressive bifocals or multifocals allow a graduated increase in power towards the reading position. The downside is that looking too far to the sides causes astigmatic blur. There is a central zone here which does not have this effect. We are now going to Chapter 4, Magnification by Lens Systems. Here we see a diagram where we show only chief rays from the top and from the bottom points of an object forming an image. We know that each of these points is giving off many divergent rays, which are then refracted to convergence by the lens, but we are only showing the single chief rays so that we can draw similar triangles and calculate image versus object size. The ratio of I versus O is called the linear magnification. And the linear magnification I over O is equal to the distance V divided by the distance U. Linear magnification is also known as transverse magnification or lateral magnification. Another type of magnification is angular magnification. In its simplest form, we simply move an object closer to the observer so that the angle subtended is larger. The observer, however, has to be able to focus on a nearer object with more light divergence. Here we see that the image has linear magnification compared to that of the object as in the previous slide. In this three-dimensional depiction with a z-axis, we now see that there is also a depth to an object. The depth, however, increases with the square of the height. The axial magnification is therefore equal to the square of the linear magnification of an object. This causes an increased sense of depth and stereopsis of objects. Here we show a simple magnifier in which an object is placed behind a lens at the primary focal point away. An observer to the right can then view the image. An object that is located 25 centimeters away without any intervening lens creates a certain angle. The tangent of this angle is equal to the opposite over the adjacent, which is the height over 0.25 meter. In this case, we have the same object located at the primary focal point of this lens. This subtends an angle alpha prime. The tangent of this angle is equal to the opposite over the adjacent, which is now h over f, the focal point of this lens. We can then take the tangent of a prime, divide by a, and get the magnification, comparing the visual angle of this situation with this one. With a little bit of algebra, we end up with magnification equals 1/4 of the power of the lens. For small angles, A and A prime, the tangent of these angles is approximately the same as these angles, so that the angular magnification, A prime divided by A, is approximately equal to 1/4 of the power. Let's say that we had a 10 diopter lens here so that the primary focal point was 0.1 meter away. 0.1 meter is much shorter than 0.25 meter here. The visual angle, therefore, will be larger, and the observer here can benefit from seeing an image with a larger visual angle with this lens than would be visible from 25 centimeters away without this lens. Another added benefit is that the outgoing rays are non-vergent and therefore require no accommodation. The outgoing rays are non-vergent because the object is at the primary focal point of the lens. Angular magnification can also be accomplished with an afocal telescopic system. Afocal because the incoming light from very far away is non-vergent, and the outgoing light will also be non-vergent, but the visual angle of the outgoing light will be different from the visual angle of the incoming light. The ratio of these visual angles is equal to the magnification, outgoing angular size divided by incoming angular size. When one of the lenses is a plus lens and the other is a minus lens, we have a Galilean telescope. The condition that must be met for a telescopic system to operate in this manner is that the secondary focal point of the objective lens must be in the same plane as the primary focal point of the eyepiece. Here we show the rays from the bottom of an object that is far away, refracted by the first lens, and then refracted by the second lens. Incoming light is non-vergent, outgoing light is non-vergent. The same can be said of rays coming from the top of the object that are far away, that are at an angle theta to the horizontal. These rays are also refracted by the first lens and then by the second lens, so that the incoming and outgoing vergences are 0. Note that in both our top and bottom object that the first lens converges the rays, which would ultimately reach the secondary focal point of this lens if the second lens were not there. This also happens to be the location of the primary focal point of the second lens, so that this virtual object at the primary focal point of the second lens has outgoing non-vergent image rays. Because f2 of the objective lens is in the same place as f1 of the eyepiece, we have met the condition here. Secondary focal point of objective must overlie primary focal point of eyepiece. We will now have the effect of an afocal telescopic magnifier. As drawn here, it would only work for distant objects that approximate non-vergent rays as they reach the telescopic system. Here we put the two parts of the diagrams here in one, so that we see the horizontal rays coming from the bottom of the object and the angulated rays coming from the top of the object that are far away, that has angular size theta, leaving the system with an angular size theta prime, which constitutes a magnification. Here we see another afocal telescopic system. This time, both lenses, objective and eyepiece, are plus lenses. This is called an astronomical telescope. In this case, the non-vergent rays are coming into the objective, which are then focused at the secondary focal point of the objective lens. This point is also the primary focal point of the second lens, so that the rays, divergent rays coming off, will then give off non-vergent image rays. Because f2 of the objective is the same place as f1 of the eyepiece, we have met the condition for an afocal telescopic system in which incoming and outgoing rays are non-vergent. Here we see the rays from the bottom of the object, rays from the top of the object at an angle theta, and here we see the combined diagram of the rays from both parts of the object that are far away. The object rays have an angle theta, but the outgoing rays have an angle theta prime, which constitutes a magnification. In a telescopic system, the magnification is equal to theta prime over theta, which is equal to minus the power of the eyepiece divided by the power of the objective. We can derive this formula using the gray triangle here, shown here, and the green margined triangle here, shown over here. We can use trigonometry to develop the formula as shown.